Welcome back, ChemStars. We're on Chapter 3, Video 3, looking at pages 4 and 5. So here is our I can statement. So I can determine the charge of a proton, neutron, and electron, and differentiate between the mass and charge of each particle. So what are those keywords? Proton, neutron, electron, and looking at mass and charge. Okay, so make sure you take a look at those key vocab words. So protons and neutrons. If there were negative particles, then there must be positive particles as well to account for the atom being neutral. So atoms are neutral, and they are made up of smaller positive and negative particles. So the proton is that positive particle. A lot of times in class, we'll abbreviate by saying P plus, so P for proton, plus for that positive charge. Now, it has a mass of 1.673 times 10 to the negative 27th kilograms. You don't really need to know that. We were able to figure that out through some experiments, but what we usually say is that the mass is equal to 1 AMU. And AMU means atomic mass unit. So one proton, instead of using this really tiny number, we just say one proton has a mass of 1 AMU. So one proton's mass is 1 AMU, just to make things simpler so we're not dealing with crazy numbers. Here is the most important thing you will probably learn in all of chemistry. The number of protons in the nucleus determines the atom's identity, and it is called the atomic number. So protons in the nucleus gives it the identity, and we sometimes will abbreviate atomic number as AN, or I'll sometimes write like a number, atomic number. Usually you'll see AN for atomic number. Neutrons, which are also in the nucleus, neutrons were discovered by Chadwick in 1932 in England. No charge, and they have a mass of 1.675 times 10 to the negative 27th. Well, what do you notice about those two masses? They are super close. They're not that far off. So we also will say that one neutron's mass is equal to 1 AMU. To abbreviate neutrons, usually I'll write N with a 0. That line there just means that it's a 0, not an O. So neutrons have a neutral charge, no net charge. Protons have a positive charge. If you want to get really into some quantum physics, protons and neutrons themselves are not the smallest particle. They are made of even smaller particles called quarks. If you are super excited into this, if you go to our lesson guide, in our lesson guide, I have linked a video about what quarks are. You can click on that link and learn more about that. That will not be covered, though, in our class. Okay, so let's go back to our video notes here. Okay, so I've given you the abbreviation for proton, abbreviation for neutron, and just to make sure that we understand that electrons, they have a negative particle, and their mass is so small, it's 1/2000th of the mass of the proton. So the mass is so small, it's essentially 0. Okay, good. Let's flip to page 5, please. So sizing up the atom. Oops. Sizing up the atom. So here's a good visualization exercise for you. So imagine a penny. So we've got a coin the size of a penny of pure copper, illustrates his concept of the atom. If we grind that copper coin into a fine dust, each speck in the pile of shiny red dust would still retain the properties of copper. If by some means you could continue to make the copper dust particle smaller, you'd eventually come upon a particle of copper that would no longer be divided and still have the chemical properties of copper. That final product is an atom. Copper atoms are very small. A pure copper coin the size of a penny contains about 2.4 times 10 to the 22nd atoms. Let's review your scientific notation. That's a really big number. It has a positive exponent. That means I need to move this decimal 22 times to the right, so I'm going to be adding like 21 zeros after this number. That is a huge number. By comparison, there's only 6 times 10 to the 9th people living on Earth. There are about 4 times 10 to the 12th times as many atoms in the coin as there are people on Earth. Now, when we get to numbers that big, it's really hard to visualize. If you could line up 100 million copper atoms side by side, they would only be 1 centimeter long, though. So I hope that puts it in perspective for you. So now let's talk about the size of the atom. So atomic radius, they can vary. Usually they're between 40 to 270 picometers. A picometer is 1 × 10⁻12 meters, so super, super tiny. Most of the atomic radius is due to the electron cloud. So this picture is not going to be to scale, but if we had a tiny nucleus, like the electron cloud would be like way off the paper. So this would be the nucleus. And this whole thing out here would be the electron cloud. This is not to scale. It's way too big. The nucleus would be much, much tinier. How big is that nuclear radius itself? The nuclear radius is 0.001 picometers. So compare those two numbers. Several orders of magnitude different. The density is 2 × 10⁸ metric tons per centimeter cubed. That is crazy dense. Remember that in our copper or in our aluminum lab, aluminum density is like 2.7 grams per cubic centimeter. So 2.7 grams versus 2 × 10⁸ metric tons. Almost all of the mass of the atom is in that tiny, tiny, tiny dot, which makes it very, very, very dense. So despite their small size, individual atoms are observable with instruments such as the scanning tunneling electron microscope. We'll see that in the in-class video. This is the basis of nanotechnology. So if you are still having trouble visualizing how big an atom is, don't worry, I'll give you another example. So let's pretend that the atom were the size of the large football stadium. So one single atom. If it's the football stadium, the nucleus will be the size of a marble. So if we put a marble down at the center field, this would be the nucleus. And then this all the way out here would be our, electron cloud. Our electron cloud way out here. So what does this say about the atom? Mostly empty space. Okay, good. Let's flip to our next page now, please. Okay, so I'm going to end this video here, but in our next video, so you can see where we're going, we're going to be talking about distinguishing among atoms. What makes an atom of copper different from an atom of gold, different from an atom of hydrogen?